Let me introduce you. Okay. Good. So this went well, much better than earlier. So it's a great pleasure to me to introduce Yingnian Wu, the professor at UCLA at the Department of Computer Science, Data Science and Statistics. So he got his PhD from Harvard and then became assistant professor at Michigan and then went to UCLA, became an Amazon scholar, I think, a few years ago, and is like, I think, very well known and one of my idols, actually, because of his early work on generative models, still like inspiring me to date. So I'm like mega excited to hear about what he's up to. The title of his talk is Slow Fast Learning for Action Conditioned Long Video Generation. Very interesting topic. So let's welcome Yingnian.
Okay. Thank you, Adam. And I want to thank the organizers for organizing this workshop and also for inviting me to give this presentation. So this talk is actually based on the joint work between UCLA and Microsoft. And the UCLA team was led by Yingnian Hong, who's a PhD student at that time when she did her intern at Microsoft last summer. And Yingnian has graduated, and she will be a postdoc in Stanford. And also, I feel very fortunate to be able to collaborate with Li Juan and other people at Microsoft. So this work is about long video generation, condition on action instruction. And here we try to introduce the idea of a slow, fast learning. So especially introducing a fast learning mechanism in long video generation. So the basic task is like this. So you have the first image frame of the video, and then you are given some instructions, mainly about navigation. For example, navigation of walking or driving, or a little bit of flying by drone. And with those tasks, right? So with those instructions, then supposedly we should be able to generate the video sequences, follow those instructions very strictly. And there are also some other tasks, for example, the manipulation tasks for the robotics. But those tasks are mainly about a pick and a place. So you pick object and you place it somewhere. For example, in this first example, we have this move to the right, and we are given the first video frame. And then we are supposed to generate the video sequence following this following this instruction. At the same time, we need to maintain the consistency of the generated video sequence. So that is, the environment should be the same, and those features in the environment should also be the same, and the movement should also be very smooth. And the second one is about self-driving cars. For example, we want to change to the left lane. And again, we are giving the first video frame, and we want to generate the rest. And for the pick and the place, for example, we pick up the apple and I'll close the door and some other tasks. And so this is like a June navigation, the last one, the June navigation task. And also, we may provide the action instructions along the way. For example, for the first 10 seconds, we go forward. And then for the, excuse me. Okay, so for the next 10 seconds, and then we go left, and then go right, and back off, and so on. So maybe I can point to the, yeah, somehow the pointer. Okay.
That one's better.
Yeah. Yeah. Okay, so those are the instructions where you can give the instructions over the time. And then we also have this video planning tasks. For example, we move both cubes to the green area, and then subsequently return them to their original positions. So those are the instructions. And again, given the first frame, we should be able to generate the video sequence. So this can be used for this planning. So that is after generating the video sequences, you can use this inverse dynamics to get the action sequence. Okay. So next slides. How do we go to the next one? Sorry about that. This one, right? Okay. Let me just mention the motivation a little bit. As I said, the goal is to do this action-driven long video generation with the consistency of the environment and also the motion. The problem is that unless you have a lot of compute, usually you cannot use a very long context. So for example, if you generate the video chunk by chunk, you can generate the next chunk condition on the current chunk. Each chunk may be like 32 frames. That's so much that you can handle, and you cannot condition the past the thousands or hundreds of frames. So that's quite impossible. So therefore, when we generate the videos with a very short context, then the problem is that it is very difficult to maintain the consistency in the long video. So that's why we try to solve this problem with the so-called fast learning, inspired by this neuroscience, especially the hippocampus. So in the hippocampus, we use fast learning to memorize the episodic memory. So for example, what happened during this workshop? So we memorize this in our hippocampus with a very fast learning. And this actually complement the slow learning, which is about long time consolidation. So that is over many years for experience. You can consolidate this in the neocortex. So the evolution still maintain this hippocampus, which means this type of fast learning is very, very important. And we want to apply this fast learning idea to this video generation. So that's the main motivation. And for this, for our experiments, we collect a relatively large data set of video sequences. We collect 200K videos from different environments. For example, from the game, we let a human to play the Minecraft game and record their actions, use those actions as instructions, and also record the videos. And also we collect a lot of videos from this Unreal with text instructions and the video sequences. And then this Epic Kitchen and OpenX embodiment, which is the environment for robot embodiment. And there are also some other robotics data sets. So this gave us our training data with 200K video sequences. Okay, and then we try to learn this our model based on a pre-training model. So that is, we want to adapt a pre-training model to our data set that we collected with action instructed video sequence generation. So the training consists of two steps. One is slow learning. The slow learning stage, we try to adapt a pre-trained video generation model to all our video sequences. So here we generate the video sequences chunk by chunk. Each chunk is like 32 frames. And we employ a U-Net. Nowadays, you can also use a vision diffusion transformer. So for the U-Net, the input consists of two chunks, and then we reconstruct these two chunks. But for the slow learning stage, we have this, we always condition the previous chunk, and then we generate the next chunk, the generated chunk. So in this training stage, we always fix the first chunk at the clean video sequences in the real data. And then we try to reconstruct the second chunk using this diffusion reconstruction. So in other words, condition on the action instruction and the previous chunk, we only add noise in this diffusion stage to this the current output. Okay, and then we use this epsilon prediction. But nowadays you can also use flow matching loss to reconstruct the second chunk based on the first chunk, and also condition the action instruction. So this is a slow learning. Basically, we want to adapt our pre-training model to the data we collected, this 200K video sequences we collected. So this is slow learning, very simple. It's really just a mask generation model. So you generate one chunk at a time, always condition the previous chunk. And the key contribution is to introduce this fast learning, which was inspired by Templar in long text sequence generation. So in the fast learning, we try to memorize the whole sequence, the generated sequence, so that we can maintain the consistency of long video generation. So the idea is that you do learning while generating. So this learning happen in this process of inference or generation process. So you generate the sequence chunk by chunk. So you condition this chunk like 32 frames, you generate the next chunk. And after you generate this chunk, you start to update your fast learning parameters. And here we use LoRa for this fast fine tuning. So that is, we store the memory about the video that we generated in our LoRa parameters. And we update the LoRa parameter along this generation process. So whenever we generate a new chunk, and then we use the same unit, but then update the LoRa parameters in this unit. So the idea is that you take the input. So the input will be the first chunk and the second chunk you just generated. And then you add the noise to both chunks. And you remove the text instruction. And then you try to learn or update the LoRa parameter by a few gradient descent steps. And then you generate the next chunk, and then you use these two chunks as the input and add noise to both chunks to reconstruct, to do this diffusion prediction type of learning, and learn all the knowledge into this LoRa parameters. So this is the idea that we keep memorizing, keep updating our LoRa parameters, and then use that to memorize the generated sequence to maintain the consistency for the generation. And then, so we have this phi as slow learning parameters in this unit, and then this theta I as the LoRa parameters that keep changing along this process of generation, where I index the chunk that you generated. And then when you update theta I, and then you use this whole parameter, phi plus theta I, to generate the next chunk. Okay, so this is the idea that you merge the learning with the generation. When you generate, you also use a fast learning to memorize what you have generated to maintain the consistency. So that's a basic idea. So just a little bit of formula. I will go over this very quickly. So for the slow learning, this f of p will be the number of frames for the previous chunk, and then we generate the next chunk. So the idea here is that we only add noise to the next chunk to be generated in the training stage, and then condition the previous chunk without adding the noise. So we still use a clean data for the previous chunk. And then for this epsilon prediction, we also condition this C, which is the text instruction. And this T index the diffusion time, not the video generation time. But the point is that we always condition the clean image frames for the conditioned chunk. So this is for the slow learning, where phi is a index the parameters for the slow learning. And then for the fast learning, it is a little bit different. So this is during the inference or generation stage. So whenever you generate a new chunk, you merge the previous chunk and the generated chunk, and you noising those chunks in this diffusion learning, and you remove this text condition. So that is, we want to use these lower parameters mainly to memorize what we have generated. And then we do a few steps for gradient descent on these lower parameters, fixing this slow learning parameters. So this fast learning idea mainly to memorize this generated sequence so far. So this mimic the hippocampus function where we have this rapid adaptation of our model to the new context. Whenever we get into a new experience, we always use our hippocampus to memorize the new experience. So this here we use a Templara as a realization for this type of fast learning memorization. And we can also integrate the fast learning and the slow learning together if we have, for example, a data set for robust planning, and we want to learn those skills, but at a different context. So the skills are stored in the parameter of slow learning parameter 5, and the contexts are stored or adapted by the fast learning lower parameter. So the idea is that we have those video sequences with those action plans. And then for each video sequence, we estimate their lower parameters along this sequence for generation. But we use a real video sequence in the training stage. So we keep updating the lower parameters. And then at each generation iteration for the lower parameter, we fix those lower parameters, and then we try to learn the global parameter phi. So that is this parameter is actually the combination of both the slow learning parameter and the fast learning parameter. So we use this as give us a loss. But when we try to learn this slow learning phi to represent a manipulation skills, for example, then we only update the phi and fixing those data, which are learned from this using this fast learning scheme on the real video sequences. So that is, we combine both fast learning and slow learning in the hope that the slow learning become a meta model in the sense that it can support this fast learning adaptation. So therefore, after you learn a model, this model actually allow this fast adaptation to the new environment to give us out of domain generalization. So that's a basic idea. And we then applied our method to the data set we collected and compare with those baseline methods based on this FVD or PSNR or some other metric. And our method with Templara or with fast learning actually outperformed the baseline on different metric and different tasks. Okay, so in terms of the computation overhead, actually the overhead is quite small. For example, for the average inference time, you generate one video sequence, the time it take without LoRa will be, without fast learning will be like 13 seconds. And with Templara, it will be like 13.8 seconds. So the overhead is very small. In terms of for actual memory, the overhead in memory is also very, very small. Okay, so therefore, it is actually quite practical or manageable to add this fast learning stage in this generation. And here, let me show you some examples. So this is for the slow learning examples, chunk by chunk. So it can generate quite realistic video sequences based on the instructions. For example, there's an instruction about merge the lane and the jump and the wash hands and some other instructions. And this is a June type of navigation instructions. So the generated video sequences are still quite consistent for slow learning. But still, this fast learning is very, very important actually, because when we generate the next chunk, we always condition on the current chunk, so that the memory is very, very small. So without the fast learning, without memorize what you have generated, the generated sequence usually does not have much of the consistency. For example, without temporal, the sequence become generate completely hallucinate to some new environment. Sometimes you see the environment completely changed with all those like instructions, go ahead, go back, and go forward, those type of instructions. So the point is that to generate a coherent, consistent video sequence, you actually need to accumulate your knowledge of what you have generated and what's underlying environment. Similarly, for those examples, so if you use temporal as fast learning, the generated sequences tends to be very consistent. Okay, those are some other examples, and you can see that without fast learning, the sequence completely hallucinate to some new environment. And the same with those like planning tasks. So as I said, to deal with those manipulation pick and place tasks, we use both fast learning and slow learning. And we learn this slow learning model to support the fast learning, to adapt to this new environment. And for this type of video generation, after generate the video sequence, we can use the inverse dynamics to get those action sequences. And without temporal, it cannot follow the instructions very accurately, sometimes get completely wrong video generation. But with temporal, usually it can remember what it did. For example, you pick up a object, right? And then you moved it somewhere and you want to place it back to where it was. So therefore you need some good memory to memorize where the object was and then place it back. So this is accomplished by the fast learning. And here are some other examples with and without fast learning. And here are some qualitative examples for planning. So here the instruction is actually very long. So you are given, for example, the first frame, and the instruction is proceed to the pole and then navigate to the tree. Subsequently, return to the original point by retracing the initial path. So you need to go back the initial path. So therefore, some form of memory is very, very important. And with fast learning, we can actually accomplish this task very easily based on the first frame. And the second one is also quite complex. So you are given the first frame, and then the instruction is move both cubes to the green area, and then return them to their original position. And after that, put the second cube where the first cube was in the green area. So this also require quite a bit of memory for the video generation, and the fast learning proved to be very, very important. And for those type of long horizon planning tasks, we also compare with baselines for different environments. And our method work quite well for FVD, for the generated video sequence. And also we we measure the performance based on the distance from the waypoints for the planning, also perform very well. Okay. And then actually what we really want to do is to do this video navigation. So the idea is that you have a random walk, like a policy, exploration policy, and then you are given this video like sequence. And then supposedly you should be able to form a internal map, the so-called cognitive map of the environment. And then that will guide your navigation. So you are given the current frame where you are, and then you want to have a sequence of actions, move forward, move left, and move backwards, and so on, to go to the goal frame. So that's this task is quite difficult, and we are trying to accomplish that task in our current work. But at this point, I think maybe I want to expand a little bit about how much time I have? The broader context about the generative model for computer vision. So currently, we mainly use a generative model for the purpose of image and video generation. And we may also want to use synthetic data to train our model. However, the question is whether we can use the generative model to do the inference and the learning. For example, based on the generative model, and if I give you the video sequence, you can learn the 3D environment, and you can also learn a cognitive map. And certainly you can learn the object trajectories for the purpose of planning. So that is, nowadays, it appears that the generative model is not very much for computer vision, mainly for graphics. But the computer vision can be considered as an inverse graphics. So the question is whether we can design or develop a class of generative models so that we can insert or incorporate explicit latent variables and explicit local parameters so that we can use inference and learning based on the generative likelihood of surrogate to guide us for planning or with the reward or value model, we can do those planning after learning from the video sequences. And this actually is related to what I call the four time scales of the computing. So in the fastest time scale for millisecond, we have the reaction reflex. This is mainly based on feed forward. Sometimes it is called fast thinking or system 1. And in the second time scale, we have planning, reasoning, and mainly we want to infer some latent variables from the model. And this is called the slow thinking or system 2. This is mainly in the prefrontal cortex. And then we have the third time scale, which may be from minutes to hours. So we want to develop cognitive map or episodic memory. So this is mainly based on fast learning of the local parameters and usually happen in the hippocampus. And then we have this long-term consolidation where we have global parameters and we use slow learning. This mainly happen in the neocortex. So currently in our model of the so-called digital intelligence, we mainly learn this stage 4 long-term consolidation, and then use it for this scale 1 for this feed-forward reaction. However, we do not really have explicit like a scale 2 and the scale 3 for this planning and also fast learning. So it is much desirable to have explicit planning and fast learning for out-of-domain generalization, because this really just a matter of adaptation. But currently, the model, we only learn this long-term consolidation model, and we use a residual net or residual stream, which basically learn a iterative algorithm, implicit algorithm, to cover this scale 2 and the scale 3. For example, scale 2, like planning, is covered by the residual stream iterative algorithm, and scale 3 is mainly covered by this in-context learning. However, those learning are not really, they can perform very well in domain, but their extrapolation ability of this out-of-domain performance can suffer. However, if we have more explicit algorithm in step 2 and step 3 for this slow thinking and the fast learning, then we can actually deal with a much novel situation to adapt to new environment. So in our recent work, we studied this hippocampus learning for the place cell and gray cells. So for the place cells, we have those different cells and they fire at different places. So this is used for navigation. And we recently developed a model for place cells, where we assume the place cells form a embedding, and this embedding actually preserve the proximity. So here, X is a position and Y is another position. And under a random walk exploration, we want to use this embedding to preserve this adjacency measured by this conditional probability at a different time scale. So that this can enable us to do this planning very easily. So only use local exploration data, we can learn those place cells, and then we can plan very sophisticated paths in the maze. And if we change the environment, then our method can adapt to this new environment very quickly by fast learning, and then plan this shortcut. So therefore, this work, we try to have explicit fast learning algorithm and also explicit planning algorithm instead of just delegate everything to the residual stream or residual net. And we also developed the model for grid cells, which serve for this coordinate. Okay, and for the okay, I will So so the point is that we want to develop models that has the ability for explicit planning, and also the understanding and reasoning. So recently we also developed this latent thought language model. For this language model, where we incorporate explicit latent variables in the language model, and then for each paragraph or each chunk of the text, we then infer the latent variables, and then reasoning then can become this gradient-based algorithm in the latent space, which can achieve much more efficient learning and reasoning. Okay, so just to conclude, so here this workshop is about the generative models for computer vision. And currently, as I said, we mainly use generative models for generating interesting videos or images. Really, we are not really using this for computer vision. Perhaps we can develop a generative model so that it can support both the reaction and the planning, and also forming the cognitive map with a capacity for both explicit planning and explicit fast learning. And the work I just presented for fast learning is only the initial step to make this type of different time scales of computation more explicit. Okay, so I will stop here. Thank you.